Ladies and gentlemen, good afternoon. The title of my study was study of behavior influenced by trend temperature rising during trend breaking. The presentation have 4 parts: background, simulation models, results and discussions, and conclusions. Let's look first into the background. Trend breaking is widely used on fluid trees and subway trees, which results in the considerable temperature rising on wear tread. The high temperature affects material properties, coefficient of friction, and contact conditions, and therefore affects wear. In the study, the numerical models are established to simulate wear, considering the temperature effects on the following factors, such as elastic modulus, tensile strength, hardness, coefficient of friction, size of contact patch, and division of adhesion slip zone. Let's move on simulation models. The physical process of trend breaking is widely used on fluid is that weakening kinetic energy is turned into the friction heat, which is transmitted to wear tread and brake shoes. The finite model is this: the conditions of heat flux boundary and convection boundary are taken into consideration in this model. The emergency braking of heavy haul trains is simulated in this paper. The results show that the highest temperature reaches 300 degrees Celsius. Now, we have got the temperature during braking, and the microscopic theory of metallic quantity indicates that temperature have direct impacts on elastic modulus and tensile strength. On the one hand, contact conditions depend on elastic modulus and coefficient of friction. On the other hand, the wear depth depends on contact conditions and some physical quantities, such as hardness. Both will affect wear profile. Based on a simple model and classical methods, Liu obtained the relationship between elastic modulus and temperature as this formula. The results as this figure shows that elastic modulus decreases by 15.6% when tread temperature reaches 300 degrees. Many experimental results of tensile tests at different temperatures have a similar trend, that it slowly drops with temperature below 400, sharply drops after 400, and slowly drops after 600 degrees, because the maximum temperature is about 300 degrees. So we can assume there is a linear relationship between tensile strength and temperature. And the maximum and the tensile test of high-speed wear steel has been made by Chen. And then the relationship between tensile strength and temperature can be obtained by fitting this experimental data as this figure, as this formula. The results show that tensile strength decreases by 25% when tread temperature reaches 300 degrees. According to the conversion tables of hardness and tensile strength values and the wear hardness measured values, we can determine the relationship between hardness and tensile and temperature as this formula. The results show that hardness decreases by 26% when tread temperature reaches 300 degrees. Following is about coefficient of friction. Popov investigated coefficient of friction in the visual system and put forward it can be calculated as a function of elastic modulus and tensile strength. Bringing elastic modulus and tensile strength into the formula, and then the relationship between coefficient of friction and temperature can be obtained by as this formula. The result of this figure shows that the coefficient of friction decreases by 4.8% when the temperature reaches 300 degrees. Next is a Poetic contact model. Firstly, the size of contact patch is calculated based on Hertz theory and this formula, and the relative sliding velocity is calculated according to steady state rolling as this formula. In the dynamic simulation, the contact forces are calculated using calculus simplified theory for the tangential problem and the Hertz theory for normal problem. Besides, the Coulomb's friction law is introduced for the division of adhesion slip zone. Finally, the wear depth can be calculated with according to a chart wear model as this formula, where the K is wear coefficient. It depends on contact pressure, hardness, and the relative sliding velocity. Based on the available test results, a wear map has been made by Olofsson as this figure. It can be said that the size of contact patch, hardness, wear coefficient, and the relative sliding velocity are influenced by temperature. Let's move on results and discussions. The longitudinal croppage is 0.15%, lateral croppage is 0.05%, and the spin croppage is 0.3 per millimeters. Firstly, the size of semi-axis and the area of ellipse are calculated in this table. The results show that the size of contact patch increases with temperature because elastic modulus decreases with temperature, which leads to the weakening of material's ability to resist deformation. Ultimately, results in the increase of size of contact patch. This figure is the comparison of size of contact patch at normal temperature and maximum temperature. The results show that size of semi-axis and the area of ellipse increases by 5.8% and 12% when the temperature reaches 300 degrees. This figure is the maximum contact pressure at different temperature. The results shows that it decreases with temperature because of the increase of size of contact patch. And the result, and it decreases by 10.87% when the temperature reaches 300 degrees. The contact patch is divided into adhesion zone and slip zone according to Coulomb's friction law. Because the tangential strength, the coefficient of friction, and the contact pressure all decrease with temperature. So the influence of temperature on division of adhesion slip zone should be studied with the method of quantitative analysis. And this figure is the area of slip zone at different temperature. The results show that it increases with temperature and increases by 11% when the temperature reaches 300 degrees. And this figure is the comparison of division of adhesion slip zone at normal temperature and maximum temperature. Now, let's look into the wear coefficient. The wear map, as this figure, is divided into 4 parts. Black stands for regime 1 and regime 2. Blue for regime 2, black stands for regime 1 and 3. Blue for regime 2 and red for regime 4. Especially, the red 4 is devastating wear regime, where wear coefficient values is dozens times than others. This figure is the relative sliding velocity and different temperature, and this figure is the combination of contact pressure and hardness. And then we can determine the wear coefficient distribution as this figure according to relative sliding velocity, hardness, and contact pressure. The results show that at leading edge of slip zone, the wear coefficient is in regime 1. At trailing edge of slip zone, the wear coefficient is in regime 2. And in other positions, the wear coefficient is in regime 4. This figure is the comparison of wear coefficient distribution at normal temperature and maximum temperature. The percentage of different wear regimes are quoted in this table. Although contact pressure, hardness, and relative sliding velocity all decrease with temperature, but the drop of hardness is greater than the drops of contact pressure. So the percentage of regime 4 increases with temperature, which leads to aggravation of wear. Finally, we are looking into wear depths. On the one hand, the changes of hardness wear coefficient and the size of contact patch with temperature will aggravate wear. On the other hand, the changes of relative sliding velocity with temperature will reduce wear, but the growth is greater than drops. So the temperature rising will aggravate wear. This figure is a comparison of wear depth on a contact patch at normal temperature and maximum temperature. The maximum wear depth at this figure shows that it increases with temperature and increases 28% when the temperature reaches 300 degrees. At the last, we can obtain the radial wear distribution across the profile by summing up wear depths along longitudinal direction as this figure. The results show that radial wear increases with temperature, and the maximum radial wear increases by 25% when the temperature reaches 300 degrees. At the same time, the wear rate in lateral direction increases by 5.8%, because the wear depth and the area of slip zone increase with temperature. Last section is about conclusions. A wear model considering the effects of temperature has been established and used to simulate wear. The results show that first, the area of contact patch and slip zone increase with temperature. Second, the wear depth increases with temperature, and the maximum wear depth increases by 28%. Third, the percentage of wear coefficient drops in the devastating wear range increases with temperature. Last, the radial wear and wear rate in lateral direction increase with temperature, and the maximum radial wear and wear rate increases by 25% and 5.8%. That's all. Thank you very much for your attention.